And we can see that if we go from this point to this point, since the curve is concave up, this point is going to be lower than it would be if it was a straight line, right? I'm leaving that intuitive. I mean, we can make that as rigorous as we want to, but there's a limit to how much we want to do here. So it's not hard to understand. It's a little hard to prove it, and I'm certainly not going to ask you to do that. Okay? But we see because of the concavity, because this is concave up, this point has to be below this line, and this point has to be below this line, right? So we conclude that the area corresponding to the refined partition is less than the area due to the original. Okay? Now the question is, where's the curve? What's the area under the actual curve? Is it more or less than the area under this refined partition? Well, what if we refine the partition again? Okay, what if we cut each of these intervals in half? It's not going to be as easy to see, but the same thing is going to happen. Okay, the area is going to be less, but in every case, I'm going to trace over this curve, if I can see around my arm. The curve is always underneath the trapezoidal approximation, if we're concave up. If we're concave down, well, I'm going to ask you for homework, but it's pretty obvious. Okay? So, this is still the case. So I can say the curve always lies below trapezoidal approximation, doesn't it? Because it's concave up. Okay? Well, what we have is if we, let's say, just subdivide this, let's just say we keep cutting the intervals in half, although we could subdivide it any way we want. Let's say we just keep cutting them in half. Okay? Each time we cut the intervals in half, we're going to end up with less area under our trapezoids, right? Because the trapezoids are always below what you had in the previous partition. So,
you in this building? Or?
For concave up curve, every refinement leads to a lesser total area, right? We see that pretty clearly? Okay, those pictures kind of show it. Okay? Now, when I say for concave up curve, I'm not being real specific what the concave up curve, there's a little more to it. The concave up curve also has to be above the axis. And certainly graphs can go below the axis, but if we understand for graphs that stay above the axis, we can easily modify our arguments. And we're not going to worry too much about that. Get this idea down, I'm going to be real happy. So for concave up curve, every refinement leads to a lesser area. Okay? The area is always greater than that. Use the word of, and it's the wrong word to use. Beneath the actual curve. Okay? And we've seen why that is. These pictures show pretty clearly. We want to think about it to really understand it. Okay, area is always greater than that beneath the actual curve. So what's our conclusion? Our total trapezoidal approximate area will approach the actual area under the curve. Okay? In such a way that the difference between the trapezoidal approximation approaches 0. Now that's a fairly sophisticated mathematical argument, very similar to the argument you use to define the integral in calculus. I'm not going to give you that argument, but one big thing we want to talk about here is areas under curves and slopes and what they mean in specific situations like the flow experiment, like the pendulum, etc. Okay? And also how some of the behaviors of the trapezoidal graphs give you insight into the way the functions themselves behave. okay? There's a huge amount of insight in here, okay? Vincent loves these trapezoidal approximation graphs, even more than I do, and I kind of invented them. It's not really an invention. I mean, it's essentially what you do when you do approximate calculus. But the labeling and stuff, you know, something I decided I wanted to use a long time ago. Okay. And, yeah, they haven't given me a Nobel Prize for it yet, so they probably don't like it. But anyhow, get the idea? Okay.